Hello everyone, welcome to today's video, new video, new project. And today's project is a bit different from previous ones because I'm not going to explain you a very precise project, a very precise topic, but instead the video is divided in three chapters, and for each chapters I'm going to take a different point of view on a very generic theme that is related to physics, physical world, but also mathematics and in particular geometry. This common theme is about the equilibrium of conservative systems of particles. I think we can jump right into the first chapter, where I will give you a much more detailed description of the problem. So here we are with the first chapter, and as you can see I'm going to use this document where I've written down some notes to organize the speech, and it helped me in introducing you in a better way to the main topic of today's project. So let's discuss briefly some thoughts on the equilibrium of conservative systems of particles, written by myself in September 2024. So here there is the problem, and this is the most generic formulation of the problem you can get. It is the most generic, and throughout the video, in the second and third chapter, I will consider and study some specific cases, so by simplifying some hypotheses. But of course, just to start, I needed to introduce you to the most generic description of the problem. So, given a conservative system consisting of n particles, so n is the number of particles. These particles are punctiform, so they have no rotational inertia, and we are not interested in that side of the physical analysis. And the system is conservative, so this one is the first strong condition, because if a system is conservative, it means that you can apply the mechanical energy conservation principle, and it also means that in theory you should be able to define a potential energy, so a scalar function that is associated to the field of external forces acting on the system. So consider that in general it's not easy at all to provide an analytical description of potential energy for a generic system of particles, whereas this task gets a bit easier if you focus on a single particle. But you will see it better in a few minutes. So, given a conservative system consisting of n particles, these particles are not completely free to move in the two-dimensional or three-dimensional space we are working, but I want them to be located on a closed, simple, regular, and perfect constrained domain. So, by constrained domain, I mean this thing. So, these are two examples, one in 2 dimensions, we are in a plane, the other in 3 dimensions. And constrained domain is basically a mathematical tool, a mathematical object that applies external forces on the particles of the system, and these external forces are basically constraint forces, and they are necessary in order to satisfy the constraint equations. So the idea is that you have these particles, you have your system, your conservative system, but you want to bound this system in a certain way in order to control it both in the space and also in time. So you bound it on a constraint domain, and therefore you can define a certain set of independent constraint equations, and in order to satisfy these equations you need constraint forces, and constraint forces are exchanged between the particle and the constraint domain. So this constraint domain needs to satisfy 4 precise characteristics four precise conditions. It has to be closed. So closed means basically that it divides the space in two distinct set. So in this case, you have clearly here a closed path and you have a closed surface. Then it has to be simple. So simple means, again, from a very intuitive point of view, it means that you don't want to have any compenetration in the surface or any intersection of the curve if you work in two dimensions. Then it has to be regular. So regular again means that you can evaluate for each point, you can evaluate one and only normal versor to the constraint domain. And in the end, it has to be perfect. So this last condition is strictly influenced by the first condition about conservativity, because basically a perfect constraint is a constraint that applies constraint force that is always orthogonal to the virtual displacement of the particle. So it basically means that you are not considering friction, you are not considering any other non-conservative effects that you might have in the real world. So these are the hypotheses. Notice that these four conditions, so closed, simple, regular, and perfect constraint domain, basically apart from the last one about perfect, that is not that realistic. Like in real world, you always have friction and non-conservative, non-linear effect. These three conditions are basically saying that I want to define the constraint domain in such a way that I can reproduce it in the real world, because if a curve is closed, simple, and regular, it means that you can create it in the real world with a good margin, with a very small error. So, of course, this is why I chose these three conditions, because I want to study something that can be somehow reproduced in the real world. So, given these hypotheses, the question is it always possible to define at least one equilibrium configuration of the system? So, this question is essential, and the answer to the question, in theory, should always be yes. So, it should be true. It should be always possible to define at least one equilibrium configuration of the system in this given hypothesis. The fact is that proving that this answer is always true for any given scenarios, it's not easy at all. At least for me, it wasn't an easy task. But the interesting aspect is that if there is at least one scenario, one system, where it's not where you can't describe any equilibrium configuration. So if this question and the answer to this question is false for at least one configuration, one system, then it means that you no longer have a conservative systems, because it means that for any given configuration of the particles, you will always have at least one global force applied to at least one particles that is not new. And this means that you will always have at least one particle that is accelerating. So you are always increasing the kinetic energy of the system, and out of nowhere, actually, starting from a conservative hypothesis, starting from a conservative system. So, of course, the answer to the question has to be true. But it's just interesting to notice what could happen, actually what means to study this kind of problem, and what happens if the answer is no. So I think it's a question worth to formulate. So here we have some degrees of freedom. Again, don't give to this noun like the typical connotation derived from classical mechanics. So in this case, with degrees of freedom, I just mean 3 independent features of the system that change the system, that are directly that influence directly the system and are independent one from the other. So the first degree of freedom is, of course, the number of particles and their intensity in terms of mass, charge, or whatever. Then the second factor you need to consider is the shape of the constrained domain. And the last factor is the nature of the interaction. This interaction, we want it to be a conservative interaction, so of course I want to work with conservative field forces, such as gravitational force, elastic force, and electrostatic force. But notice that for today's project, I'm not that interested in evaluating the stability of the equilibrium. So you might know that once you find an equilibrium configuration, you might ask yourself, is it stable or unstable? And most of the time it's useful to study stability because it gives you many more informations from an engineering point of view, but also a more analytical point of view. In this case, for today's project, I'm not that interested. It's not that relevant because I want to answer to this question, and the question is not about stability. It's about, is there equilibrium or not? So, but just to try to discuss all these thoughts, it's important to notice, at least from an intuitive point of view, without proving anything, that if you work with field forces that are always attractive, such as gravitational force, you are likely to end up studying equilibrium configuration that are unstable, because basically if the field force is always attractive, you play with the sign of the potential energy and you end up having a maximum of the potential energy for your equilibrium configuration, because gravitational force and in general attractive field forces tend to collide all the particles one with the other, and therefore if you have an equilibrium configuration where the particles have a certain distance one from the other, it is likely to be an unstable condition. Whereas if the field force, conservative field force, is always repulsive, which is the case of electrostatic force if all the charges have the same sign, if that is the case, you are likely to work and to study an equilibrium configuration that is stable. Again, because in that case you are working on a minimum of the potential energy function. In other cases, such as elastic force, the field is not always repulsive or attractive, but it depends on the distance between the particles. So this was just a little note, a little parenthesis to that I think it was interesting to notice. Then moving on, we have this formulation. So here, as you can see, I wrote the equilibrium condition for the ith particle. So again, I'm focusing on a single particle, and I noticed that you can apply the Newton second principle, dynamic second principle, and you have that the acceleration of your particle multiplied by its mass is equal to the global amount of forces that are applied on the particle. So these forces usually, at least from a Newtonian classical point of view, are divided between external forces, and here we have the global external force applied on the particle, and internal forces. Internal forces are due to the interaction among all the particles, so you can describe them using this sum notation. But we notice that if we work on a vincular domain, we can describe the system in a much more meaningful way, because basically you can rewrite this expression in this way so as to underline the importance of the interior force interaction. And because basically you notice that following this drawing, or this one, they are equivalent, you have that in black there is the normal, the versor normal to the vincular, to the constrained domain in black, and then in blue you have the interior forces exchanged between all the particles, and in red you have the constraint force that the constraint domain applies to the particle. So in the end you have that in order to satisfy the constraint condition, the global force applied on the particle is always tangent to the constraint domain. So you can use this information, the normal versor information, in order to express this quantity right here. And this is exactly what is going on here, where basically the total global force exchange is written in this new way. And here you highlight that in order to have a contribution different from zero, the interior force has to be not parallel to the normal versor. If it is parallel to the normal versor, then this cross product is equal to zero and you have a zero contribution. So this means that if you want to have if you want to evaluate the equilibrium condition for a single particle, so let's say you want to study the equilibrium of just a single particle of the whole system, then it is in equilibrium, so it is fixed in the space and time, if and only if the whole force acting on the particle, actually without considering the, only focusing on the interior forces, so without considering exterior forces, constraint forces, but it means that the whole interior force applied on the particle has to be parallel to the normal versor referred to that certain point of the constraint domain. So if you manage to get this condition for all your particles of the system, then you have the equilibrium condition of the system satisfied, and your system is in equilibrium, and you answered this question by saying yes, there is at least one equilibrium configuration. So just to close this first chapter, that was just an introduction to the problem. Here I basically wrote down in a more explicit way the interaction between particles in the case of a repulsive electrostatic force. So in this case we have, I think you know that the interaction is described by Coulomb law, and if it is repulsive, it means that this quantity right here is always positive, and therefore this term is positive, and here in this case I didn't write, I preferred to write in an explicit way the versor of the force, but it's not that relevant. So the idea is that you describe the force in this way through Coulomb law, and then you have the potential energy associated to the particle ith of index I, and you can define it in this way. So in this way you are considering that, again, remember that actually always the value of potential energy is arbitrary, because usually you want to evaluate its variation, so it doesn't really matter its absolute value. In this case you assume that potential energy gets equal, assumes value 0, so is null if the distance between the particles is infinite. So here you can describe the mechanical energy of the single particle, and you end up having this formulation. I just want you to reflect on the fact that for the Dirichlet-Lagrange theorem, if you have a conservative system, which is the case, and if you have a minimum point of the potential energy, that minimum point is associated to a configuration of stable equilibrium. But the fact is that if we consider this example, here you might have a stable equilibrium if you manage to maximize this term right here, so the distance between two functions. Oh, here there is a little error because there is 2, 1, but it should be I and J. Yeah, a little mistake. So the fact is that if you manage to do it, it doesn't mean that the kinetic energy is null. And this is pretty important. Like if you start from a random configuration where your potential energy is not minimum and your kinetic energy is 0, it makes sense. Then you let your system evolve spontaneously in the configuration associated to the minimum level of potential energy. And when the system reaches this condition of equilibrium, if at the beginning the kinetic energy was null, it means that necessarily for the conservation, the mechanical energy conservation principle, it means that if the potential energy has decreased, then necessarily the kinetic energy has increased. So it means basically that you still have equilibrium, but the system, as soon as it is conservative, so as soon as there is no friction, the system is not fixed, like the particles are not fixed in the space and time forever, but instead they are oscillating, moving around configuration of equilibrium, a position of equilibrium. So again, this is pretty intuitive. It doesn't change, of course, the description of the whole system, but it's important to notice this little detail, because you don't have to basically confuse things related to acceleration, which is this equilibrium condition, with things related to velocity and displacement. So, saying that, I think that the introduction is finished and we can move into the second chapter, that is about the study and the simulation of a spontaneous evolution of a cloud of charges, repulsive charges, in a sphere. So let's jump into the next chapter. So here we are with the second chapter. Now that I formulated the problem, ideally, I would like to prove it for any given system, but this task is truly difficult. I think it is almost impossible, although you might find a way to do it using the main feature of conservative fields, that is about their irrotationality, and therefore you might find something interesting about circuitation and so on. But I'm not that good in mathematical and analytical thinking to do so. So instead of prove this statement, prove this generic formulation for any given system, there are some alternatives, and there are mainly two options. So the first option is clearly to simplify a hypothesis, and in order to simplify the system, so introducing new hypotheses and then trying to prove the statement, this theorem, at least for this simplified case. And this is what I'm going to do in the next chapter, which is also the last chapter of the video. Whereas the second option, that is actually what I want to study for in this chapter, is about exploiting the basically the computational power of modern technologies in order to get a simulation of the system, not necessarily of its dynamic, but only of the distribution of internal forces. So just to basically use this simulation to see if the system spontaneously evolves towards its configuration of equilibrium, and therefore see if there is actually a configuration of equilibrium. So, of course, by doing this, you are not proving anything again, but at least you get an idea, a pretty realistic and valid idea of the existence or not of your equilibrium configuration. So this is what we are doing here. The idea is to study a specific case, which is the three-dimensional system where the constraint domain is a sphere. So basically we want to simulate what happens if you let a generic cloud of repulsive charges evolve on a sphere. So this is the constraint domain. It's not that important to visualize it, also because the only really important feature of constraint domain is its shape, and so a sphere identifies univocally a shape, and it's not relevant its origin nor its radius. So I'm hiding this sphere, and for today's video, in this chapter, of course I'm not going to explain to you the whole code that performs this simulation, because it would take me like 2 or even 3 hours, but I will just show you the inputs and outputs of the algorithm. So starting, of course, with the inputs, you have n equal 3, which is the dimension of your space. So 3 means that you are working in a three-dimensional environment. Of course, you can work in a b-dimensional environment, but the more interesting analysis came when you work with dimensions major to 3, like in 4 or 5 dimensions. Of course, the computational cost increases, but there's nothing there's nothing forbidden in when you code something. So you are free to perform simulations even in 10 dimensions if you like. But again, I'm interested in the actual results that I could somehow reproduce in real world, and therefore real world stops in 3 dimensions. So we have the radius, that again, it's not relevant. Number of points, of course, is an essential input, an essential value, because it is basically the number of particles of the system we are considering. Then you have these 3, actually 4 factors, parameters that are related to the charges characteristics. So in this case, unit charge means what is the value in terms of Coulomb, so in terms of electrostatic intensity that you want to attribute to the single charge. So in this case is 1 Coulomb. And then you have the equal charges variable. So basically, if it is true, it means that the algorithm considers a certain number of points, in this case 3 particles of the same intensity given by unit charge. Again, they are the same intensity because equal charge is equal to true. If this variable is equal to false, then basically the algorithm evaluates each charge in a random way through a random function, and the charge will be the intensity of this charge is going to be included in this interval. So these are the meanings of these 3 or 4 parameters. So this last parameter is about the collocation point of the origin of the circumference as a constraint domain, but again, it's not that relevant. Whereas here we have an important parameter, max iteration on construction. So it is basically the maximum number of iterations you want to perform. Of course, if the algorithm detects a configuration of equilibrium before reaching this value, it stops the simulation and you get the output. But instead, if the simulation is particularly slow, or if it doesn't converges to the equilibrium configuration, then the algorithm stops at the, in this case, 1000th iteration. Then you have, this parameter is important, but it would take me at least 10 minutes to explain to you what it is about. It is basically about the construction of edges and faces of your polygonal if you want the output to be a polygonal, an actual polygonal with edges and faces and not only with vertices. But you will see it better in a few minutes. And then you have these 2 tolerance values that are essential because the idea is that in order to, the logic behind the algorithm is pretty simple. So the idea is that you start from a certain random configuration of charges in your sphere, n-dimensional sphere, and then you evaluate the internal forces that are applied for each charge, and you move each charge in a certain way following a certain function that I'm not going to explain to you today. Then you move them all, and you get into the next step of the simulation. Of course, it is an iterative process. You get into the next step, you evaluate again all the forces, and you move all the charges, and so on, so on. So of course you need to define a way, a criteria to check if you are converging, if the simulation is converging to a configuration of equilibrium. And in order to do so, I define actually two criteria that are independent. So there is, we could say that there is a kind of double check between the two criteria. They are not completely independent, but they are different for sure. So this criteria, which is like lead by this tolerance value, R for stabilization error, describes the relative error in terms of stabilization. So it means that basically for each iteration of your simulation, the algorithm compute a stabilization relative error that is the maximum relative error of your force compared to the same force, actually not the same force, but the force applied to the same particle in the previous iteration. So this means that basically if you are in a certain iteration of your algorithm, you compare for each particle, you compare the force, global force that is applied to the particle to the previous force that was applied. So of course there are two vectors, so you are basically comparing the three or more or less components. And for each comparison you define a relative error, and the maximum of relative errors is then compared to this tolerance value. So basically it means that if this maximum relative error is less than this tolerance value, then you can say by good approximation that you are in an equilibrium configuration, because it means that basically for each iteration the change of your system is almost equal to zero, is really little, is truly small, and therefore you can say that you have reached equilibrium. In another way, this second criteria is not about the comparison between a previous actual and previous configuration, but the comparison is done between the actual configuration, so the force that is applied to the particle, and the normal versor of the surface of the constrained domain. And in this case we are working with a sphere, so the normal versor is actually the radius versor. This value is evaluated in terms of the tangent of the angle included between these two vectors. So there is no more a relative error, but it is actually the actual tangent. So these are the main things to know about the inputs. Then you have a lot of other things that I'm not going to to explain to you today. Yeah, let's see what happens. So we can start with three vertices, 3 points. Although, of course, we know that the output will be an equilateral triangle. So let's just verify it. And here it is, our equilateral triangle. Of course, the algorithm reached immediately after only 8 iterations. It reached the equilibrium. So now I might, here it is animated, but the animation is just 8 frames, so for the moment it's not that interesting. Now I just want to comment you briefly the output of the code. So here we have some construction parameters regarding the system. Then you have parameters on the DSF function, which is basically the function that decides how to move the particle from one iteration to the next one, and its function of the force that is applied to the particle. And then we have the proper outputs. So of course this value is the number of iteration on construction. So in this case, just with 8 iterations we reached equilibrium. Then you have the criteria that the algorithm has followed in order to find the equilibrium. So in this case, you see that we reached force orthogonality stability before reaching the force variation stability, but in both cases we were basically converging. Here you have the output of this analysis. So here on the upper side you have the recursive stability function plot, both in a linear scale, in a linear graph, and also in a logarithmic scale graph. And in both cases you see that you are basically converging to value equals 0. Whereas here on the downside we have bottom side maybe we have the orthogonal stability function, again both in the two scale graph, linear and logarithmic. And then moving on with the outputs, we have maximum of mean length is a value that is interesting if you're interested in the geometrical output and in studying the regularity or not of your polytope. And in this case the algorithm detected regular polytope. Well, of course we have a perfect equilateral triangle, so it is necessarily a regular polytope. So let's see what happens if we study some more complicated system, some more complex system. So let's move to 4 points in 3 dimensions. Alright, so here we are. Again, for the moment the convergence is pretty fast. As you can see, we get our regular polytope after only 14 steps. Let's try with 5 vertices, and we have 79 steps for the proper convergence on equilibrium. All the time okay. And this is the output. Again, it's clear that it is regular. So let's see the animation, how it looks like. So here you start to notice that we can appreciate like how the system is stabilizing itself. And actually I want to show you another parameter that is hidden in the script. So of course you need to know the script in order to know what this parameter do, but it's pretty strong. So this parameter is the famous K. Here it is K monitor. So this parameter, basically the lower the parameter, the slower the simulation is, but it is also more precise. So in this case it is equal to 0.1, and the algorithm needed 79 iterations to get to equilibrium. So let's see what happens if we increase this value to like 0.5. As you can see now, the iterations were only 50. So actually, we take less, we needed less iterations, and we still have a regular output, and the animation is even faster. But the overall precision of the simulation has decreased. So we are not being as precise as before. If I decrease this value to like 0.01, you will see that we will need much more iterations in order to get to proper stabilization of the cloud, but the precision is much higher. So let's see. You see 0.01, 181 iterations, and also the animation is clearly slower, as you can see here. Here, as always, you have the plot, and you can appreciate how we are converging to 0 in both, following both criteria. And here you have the output. So let's do some more example, and then I think we are done with chapter 2. So let's do like 12 vertices, which is always funny to see. Yeah, 12 with 0. With 12, we can still decrease k, actually increase k, like to 0.1. And it takes us 154 iterations, and again we have a regular polytope detected. So let's move to animation again, and this is the output. So of course with 12 vertices we have our heaven regular polytope, and clearly it is a configuration of equilibrium in three-dimensional space. So let's do just one last example. Of course, if you are not working with, like, let's see what happens if you work with these equal charges. So equal charges equal false, and we want the charges interval to be from 2 to 20, let's say. In this case, for sure, we won't get a regular polytope, and the simulation might need much more iterations in order to get to the equilibrium. And also the output will be something a bit messy, because it's not easy to evaluate all the right edges and faces for a not regular polytope, but let's see what happens. Remember that the maximum value of iteration is 1000 in this case, and I think we will reach it. Alright, we reach it. Let's see the graphic output in a few seconds. And here is this graphic output. So as you can see, we have no edges, because again all the charges are charged in a different way. So these are the charges, like we go from 19, 2 coulombs, 4, 5, 17, 10, and so on. So, but we can still see that the interesting and important thing is that in the end, doesn't matter if the output, the graphic output, is not that pretty, but in the end you still have basically convergence of convergence of your criteria, both in terms of stability, recursive stability, and orthogonal stability. And the animation is something like this. So you can see that the particles are moving pretty slowly and they are reaching the configuration of equilibrium. So this is it. And then of course you can play with the algorithm. You can work with 5 dimensions. Yeah, let's see what happens. Just let's put equal charges to true again. Yeah, let's try it. Again, it might take some more time. All right. Oh, here it. Oh, as you can see, it's still in 4 dimensions. So this is the output. Again, it's a projection of 4 dimensions in 3 dimensions projected in 2 dimensions, which is the dimension of the monitor. So the output is not that representative of the actual system, although you can still appreciate some symmetries of the system. And the interesting fact is that although we are working in 4 dimensions, actually 5 dimensions, sorry, is still detected a regular polytope, which is always interesting. Of course, you might ask what I mean by a regular polytope. So basically, it's a term that I have formulated on my own. And in this case, for this algorithm, a regular polytope is a configuration of vertices in your geometrical space where each vertex of the mesh sees the same mesh. So this means that if you if you evaluate the distance between your vertex and all the other vertex, and you organize these distances in a set, so basically by considering the number of distances that are equal one from the other, if this set is the same for each vertex, then it means that each vertex basically sees the same polygonal, and you have a regular polytope. This is the simplest explanation I can think about. As I was saying, the interesting fact is that we reached stability, we reached equilibrium in just 885 iterations. And this is the output. Yeah, this is the animation. Here we are working, remembering 5 dimensions, so it's not easy at all to actually just imagine what's going on. But it's still interesting to look at it and admire this simulation and the power of computational analysis. And yeah, I think we reached stability. And here we have again. All right. So I think this is everything for chapter number 2. I think we can move on to the next chapter. But before moving on, I'm going to attach to this video a short video, like a trailer of 1 minute, around 1 minute, where I show basically the spontaneous evolution of some specific cases, some clouds in 2 dimensions, 3 dimensions, 4, 5, 6 dimensions, so that you can enjoy it. So let's move on. So here we are with the third and last chapter of the project. As you can see, we are narrowing down more and more the scope of this analysis, of this study, because I've started with the first chapter that was really truly generic, and I didn't prove anything about that famous question in the formulation of the problem. Then we moved to the simulation of this specific case about a cloud of repulsive charges in a sphere. And again, the simulation, of course, helps you in doing some further evaluation, and also in trying to get some conclusion, but I didn't prove anything again. But here, finally, in a very specific case that I will discuss briefly, I managed, with the help of a friend of mine, we managed to prove something. So to basically give let's say a spark of formality to this whole study and to this whole description of the problem of equilibrium. So here we are talking about the characterization of anti-ortho-parallelism for Jordan regular curves. Again, in this case, we are working just with curves, so we are in a two-dimensional space, and these curves, of course, are our constraint domain, and they have to respect the famous four conditions, in particular the three conditions related to the geometry of the curve. So they are basically Jordan regular curves because we have regularity, and Jordan curve means that it boasts a bunch of qualities described in the Jordan theorem that is applied to curves that are simple and closed, which are the other two conditions that here are not explicitly written. So basically we are working with curves that are, again, simple, closed, and regular. This document has been written by Riccardo Dante and myself in September 2024. So here we have the hypothesis of this theorem. It's not even a proper theorem, or if it is a theorem, it's pretty brief to prove, but it is a proper characterization, so it tells a lot about some properties of these Jordan regular curves. So here are the hypotheses given: A, B belonging to R, so we have two real numbers, and A is less or equal to B. And given this function, gamma, which is a function of one proper variable, so which is a parameter. Here basically we are introducing the parameterization of this curve we want to study. And this parameter is t, and it belongs to this interval, closed interval, where a and b are the ends of the interval. And we define this function in this way. So we have two components, two independent functions that are function of this variable t, and they are two because we are working in two dimensions. So we want to we want that, again, this curve, this function actually has to respect four conditions. So it is such that it belongs to the class of order 1 in the closed interval AB. So this means that it is continuous, and also you can derive it at least one time for the first order in this interval. So you can it is basically a regular curve, a continuous and regular curve. So here we have satisfied this first condition. Then we have the closure condition. So we want that gamma A is equal to gamma B, which means that basically the output given the first input, the first end of the interval, the output is the very same of the output that we get given the last input. So actually the last end, the second end as an input. So it is basically a closed curve because we can define a certain period equal, for example, b minus a, and then by adding that period to a certain value, we always get the same output. So the curve is properly closed, and it's closed in this very interval. Like, this is the shortest interval you can define in order to track the whole curve at least one time. So touch all the points of the curve at least one time. Then we have this third condition. So given t not equal to s, we want that the images, so the output, the two outputs, we want them to be different. So basically we are imposing that the curve has to be simple. We don't want it to have any kind of intersection. And of course for all ts belonging to this open interval. So we are not considering AB because previously we said that if if t is equal to a and s is equal to b, we have that t is not equal to s, but we have this condition that is the closure condition. And then last but not least, we have this last condition such that basically we impose that the derivative of gamma in a given value t is not null, is different from the vector 0, because in this way we provide a proper description of the properties, and we don't fall in a in a particular case that would be a bit let's say delicate to work out. So given all these hypotheses, we introduce this object, which is a function. This function is a scalar function because the output belongs to real numbers, and the input, the domain, is the Cartesian product between the interval AB. So basically we have two inputs, two variables belonging to this Cartesian product, and we end up having a real number. So it's a scalar function, and in particular here you have the proper definition of f. So given t as belonging to this domain, you have that fts is equal to the norm, Euclidean norm, of evaluated for the two values of gamma. So basically f is the distance function. So f gets in input two values of the parameter that are associated to two distinct points of our curve, and in output we'll get the distance, metric distance, canonic distance, Eulerian distance of these 2 points, and the distance in this case is defined in this way. So I just make explicit this notation. So to all this, the theorem says that given all these hypotheses, we want to prove that if the gradient of the distance function is equal to vector array 0, so it's null, if and only if this relationship is satisfied. So for all t belonging to the closed interval AB, here it is actually ts, t different from s. We want that these are three arrays clearly, and we want that the distance, like the array, actually the segment associated to the segment that links the two points, distinct points associated to the parameters t and s, this segment has to be orthogonal, perpendicular to these two, both of these two terms. So the tangent straight line in t, which is tangent to our curve, and the tangent straight line in s, tangent again to our curve. So from this conclusion you might understand why we chose this special term, so anti-ortho-parallelism, because basically you are by imposing this condition, if this is true, and if you manage to prove that this condition is verified at least one time for any given Jordan regular curve, then it means that the 2 points associated to this value t and this value s, they are anti-orthoparallel, because basically the 2 tangent straight line are parallel one to the other, and they are both perpendicular to the segment that links these 2 points. And clearly it's clear that this means that if you work with a conservative system of particles made out of just 2 particles that are free to move in this Jordan regular curve, then they will spontaneously tend to place themselves in these 2 points, these 2 anti-orthoparallel points, because in this way you get that the internal forces exchanged between the 2 particles are in both cases are normal to the normal versor evaluated in that very point, in these 2 points for that specific curve. So this means that the system is in equilibrium because the global force exchanged considering also the constraint forces is equal to 0. And you end up basically respecting that famous condition that I've shown you in the first chapter. So this theorem, proving this theorem is important, because if you manage to prove it, you have basically answered the famous question we discussed in the first chapter for this specific case, of course. So for a Jordan regular curve has a constraint domain, and for conservative systems of particles made out of only 2 particles, which is not that much, but it's still a result. It's still something to start from. So let's see the proof. Basically we write explicitly the partial derivatives for FTS in T and S. So remember that this is the explicit formulation of the distance function. So basically using the basic rules of derivatives you get this expression. And you notice that here you can simplify all the factor 2, and you end up having this pretty useful compact formulation of the partial derivative. Then of course the distance function is symmetric, actually not symmetric, but you can commute t and s and you end up of course having the same result, because you are evaluating just the distance as an absolute quantity. So basically you have that the 2 derivatives are really similar one from the other. It only changes the this parameter is the only aspect that changes. Then we express, we underlined the existence of the gradient for t different from s, because basically you notice that if t is different from s, then well, FTS is greater than 0. It's a positive quantity. And this is just a little remark. And you notice that by hypothesis, gamma belongs to C1, so it is continuous and you can derive it at least one time in this interval, as always. So the two components, x and y, which are the two functions you find here, they are themselves C1 in the same interval. So therefore the derivative of first order is C0 at least, so at least it is continuous in the interval. And therefore this means that if you look at this expression right here, you notice that basically as soon as t is different from s, if t is different from s, this term, the denominator, is not null, and therefore this value assume a real finite number, real finite value. And therefore it means that as soon as t is different from s, basically also these elements, so the partial derivatives, are continuous in this domain. So in this case, actually not in this domain, but in this case we are considering a neighborhood set given the two values of t and s. Because basically here you're working on the function gamma, whereas here you are moving to the function distance. So there are two different objects, and they, of course, they referred to two different domains, and therefore the description is a bit different. But the idea is that basically it's made, everything I think it's made clear in this formulation. So the idea is that the gradient of this distance function exists for any given value of t different than s. If t is equal to s, there are some problem because here you see that this function might be no more continuous, but we are not interested in these cases because, again, if t is equal to s, it means that you are considering that the two particles are somehow compenetrating each other, and this is not realistic. It never happens in real world, so it doesn't make that much sense. And we are satisfied with this property. So existence of the gradient of this distance function for t different from s. Then the last step of this little proof is the equivalence check. So basically we have the formulation of the two components of the gradient. Remember that distance function is a scalar function, the gradient is a property of scalar functions and is a array. And here we have that the gradient of the distance function is equal to 0 if and only if the two components are equal to 0. So this means that these two terms have to be equal to 0, and in the end we get exactly what we wanted, what we were looking for, because we have that saying that this dot product is equal to 0 is equal to saying that basically this is a property of algebra, linear algebra. If the dot product is equal to 0, it means that these two arrays are perpendicular. Again, in this case, it's important to underline that we impose this hypothesis so that this equivalence actually makes sense and it's meaningful, because of course if the derivative is 0 itself, then again this is necessarily always equal to 0 because at that point the idea of relative angle, of perpendicularity and so on lose any sense if one of the two arrays is null. But again, thanks to this hypothesis, the equivalence is properly formulated, is properly written. So this is the proof. Saying that, I want to do some little remarks. So here, this image I think is really useful. I don't know if so far you have managed to imagine this concept, all the mathematics involved in this little theorem, imagine what's going on in the distance function, but here there is a pretty explicit description, representation of the distance function. So basically you have here a possible, an example of a curve that is given by this explicit formulation, and clearly it is closed, it is regular, and it is simple, so it is a Jordan regular curve. Here you have your two distinct points related to two different values of t and s, t1 and s1. Here you have the segment, so you can evaluate the distance for these two precise points. And here you have the contouring of the distance function. So as you can see, the input, the domain of the distance function is a square given by the Cartesian product made on this interval AB. In this case, A is equal to 0, B is equal to 1. Remember that given a certain curve, the parameterization is more or less arbitrary because you can always put a factor in front of your parameter and you get a new interval, a new period of the parameterization. So you get a different function but the same curve as an output, as a graph. So this is just a little note. And the interesting fact is that this is the output. So in this case, here I chose two generic points. Clearly you can already see here just from the drawing that they are not two anti-ortho-parallel points, they are two generic points. And you can see that this is basically where we are in the domain, because t is approximately equal to, let's say, 0.15, around 0.15, and s is a bit larger, a bit greater than 0.5. So this is our point, and here you have to imagine, and in a few minutes you will see it better in MATLAB. You have to imagine that there is, of course, the third axle where we plot the whole function and where we basically plot the scalar value we get as an output of the distance function. So anyhow, this is just an example, and as you can see from here we have the contouring, and basically whenever you see this concentric structure, it means that you have a point of minimum or maximum. So basically here I can see from a qualitative point of view that I have a point of maximum for t equal to 0.5 and s equal to 0. And in fact, if I put t equal to 0.5, so I'm here, and s is equal to 0, you notice that clearly these two are two anti-ortho-parallel points, because this segment is perpendicular to the two straight lines that passes through the 2 points. And the same goes with this point, which is around 0.75 and 0.25, which is exactly this case. And again and again. But I just wanted to do some little remarks on this whole argument, because you can notice that, well, first of all, as I've just said, the distance function is major or equal to 0, greater or equal to 0 for any given Ts belonging to this domain, because again we are evaluating the distance from a very classic and canonic point definition. Then we have that Fts is equal to 0 for there are many cases like where we can say that FTS is equal to 0. Of course, if t is equal to 0, because if t is equal to s, because if t is equal to s, basically we are evaluating the distance of a point from itself, so it is necessarily 0. And this is underlined in this red diagonal right here. So you see that as soon as t is equal to s, you get value equal 0. So the function assumes value 0. But not only in that case, it assumes value 0 also if t is equal to a and s is equal to b, because remember this famous condition that states that the curve is closed. So also in this case, if t is equal to a and s is equal to b, which is this point right here, as you can see it is red, and also in this case, which is the other point, if t is equal to b and s is equal to a. So we have basically this set made by the diagonal of this square and these two points, two vertices, where we know for sure that the distance function assumes value equal 0. So, last but not least, for the moment, so far, I have proven that if there is, if there are, if there are 2 points that associated to the distance function, and if the distance function has a gradient equal to 0 for those 2 given points that are associated to 2 distinct parameters, then that 2 points are 2 anti-ortho-parallel points, and they are relevant in the study of equilibrium of for conservative systems of particles. In this case, again, we are considering just 2 particles moving around a Jordan regular curve. But for the moment, it's not that clear, it's not that evident whether these 2 points always exist or not in a given generic Jordan regular curve. So the point is that, of course, you can always detect at least 2 points in a Jordan regular curve that are anti-ortho-parallel, because we notice that the domain of the distance function is a compact set. So compact means that it is closed and bound, and therefore for a basic theorem, mathematical theorem, we have that if it is a compact set and if FTS is at least C0, so if at least it is continued in this compact set, of course including the bounds, then here in this case we know that it's not only continuous but it's also derivative, at least in the excluding the diagonal, because the diagonal is associated to equal values of t and s. However, we have that necessarily there is at least 2 values x and y tilde, such that f the function, the distance function evaluated for x and y is greater or equal than the values the function assume for any given ts belonging to the domain. So this means that basically you can for sure detect 2 values x and y, so a point in this square, a point in this domain associated to a point of maximum relative maximum, actually an absolute maximum of the distance function. So then we can say that if x and y belongs to this set, actually this square domain, which is basically the starting domain minus the border. So if x and y are not like this point in this plane is not located in the border, then it means that we have here proof that the gradient exists apart from t different from s, apart from the region of the domain where t is different from s, is equal to s. So if this is the case, then necessarily if the gradient exists and if x, y tilde are a point of maximum, as we have as we have made clear here, then necessarily it means that the gradient of the distance function evaluated for x tilde and y tilde is equal to 0, and you get that x tilde and y tilde are referred to 2 points of the Jordan regular curve that are anti-ortho-parallel. Else if, of course, we have the other case. So if instead x and y belongs to the border of our square domain, so basically if x or y are equal to a or b independently, you have that there is always, you can always define, here is an example, you can always define a real number c. For example, c here, this is just an example, c equal to the mean value between x and y, such that x and y belongs to c and d, so to, again, the Cartesian product of the interval, open interval CD, with d equal to c plus t, where t is the period of your parameterization, t equal b minus a. And again, c different from, of course, a plus kt, k being an integer, so basically we want c to be different from a, different from b, and different from all the possible multiple that always get you to the same point, because remember that our curve is closed and therefore you can define an interval of values, of parameters, such that you always end up in the same point as the output is always the same. So given c exists for sure, a possible value is always this one that exists as soon as x is different from y. So in this case, you have that this time you can say, as we have said here, that the gradient exists, but this time you are no longer working in this square domain, but you're working in this new square domain CD, defined in this way. So basically you are changing the parameterization so as to move the domain around, and so as to basically make the point of maximum or minimum fall in this region, and so that it doesn't fall in the border of your square domain. But you will see it in a much better way in a few seconds. So this is the document about this characterization of anti-ortho-parallelism for Jordan regular curves. And again, this is a little spark of proof of theorem that a very close friend of mine, and I managed to develop and to study in recent times. Actually, last year, but yeah, that's another story. Now I think we can move into MATLAB so that I can show you what's going on with the function, with the distance function for some given Jordan regular curves. Yeah. So here we are in MATLAB, where I've implemented this code that allows me to get the distance function and its plot for any given curve. So of course, in order to run the script, we need the actual analytical parameterization of the curve. And I think that we can start from the simplest case, which is the circumference. And this is the typical parameterization. Remember that also in this case I'm going to considering an interval from 0 to 1. So let's run the script and see what happens. So this is the output. As you can see on the left, you have the actual curve. In this case we are considering a circumference where the center point, the origin, is at 0, 0 and the radius is equal to 1. And here on the left, that maybe you don't see that well from the YouTube video, so we'll put it like here. Alright, here on the left you have the actual plot of the distance function, and of course we can do some interesting remarks about this output. So first of all, if we move around the plot in this way, you can truly appreciate how this output is respecting all the features that we have seen in the previous part of the chapter, talking about doing some brief remarks about the theorem about anti-ortho-parallelism. So, as I've just said, this distance function is symmetric to the diagonal line that is right here. And as we have just seen, the distance functions assumes value equal to 0 if you move on the diagonal line, so if t is equal to s, and also if you are right here in these two vertices, because in these two cases you have that t is equal to a and s is equal to b, or t is equal to b and s is equal to a. So it is equal to 0, distance function is equal to 0 because again the curve is closed and a and b are the two ends of a full interval. So then, talking about this specific case, so remember we are analyzing a circumference, you notice that basically you have an infinite number of points that are properly associated to a couple of anti-ortho-parallel points. And this occurs clearly because in this case, if you consider a circle, you can consider any infinite diameter of the circumference, and the two end points of the diameter, the two extreme points, are necessarily anti-ortho-parallel. So they necessarily describe a configuration of equilibrium if, again, you consider a conservative field force and how it interacts with constraint forces and so on. So in this case, you notice that, let's zoom a bit. Sorry if there is my face at the top right corner, but it is what it is. And you see that basically the points of our square domain where the gradient of the distance function is equal to 0 are all the points belonging to this straight line that is clearly parallel to the diagonal line. And this straight line starts from 0.50. So it basically means that if we are right here, this point is associated to this diameter right here, from 0.5, that is here, because remember the parameterization goes from 0 to 1, and it is arbitrary, from 0.5 to 0, which is like the second end of our segment. And then if you move along this straight line, so basically if you increase the step of the same quantity both in this direction and also in this direction, because the slope of this line is equal to 1, is 45 degrees, as it is parallel to this diagonal line, then you get another diameter, and then another one, and you are always considering diameters of the same length, of course, as the circle is always the same, and for each of them you have two anti-ortho-parallel points. So let's now look at another bit more interesting case. So I want to show you this case, which is pretty to look at, which is this one, that it's like a flower with 5 petals. Oh, sorry, I forgot to. All right. So here we have this second case. So as you can see in this case, let me zoom it a bit more. So this is the curve, which is parameterized in this way, if you're interested, like this way. And you have, and this is the output, this is the distance function. So you notice that in this case, clearly we are not talking about a circle. So there will be a finite number of minimum and maximum of the distance function, so a finite number of couple of anti-ortho-parallel points. And for this specific case, I wanted to show you what happens when you move around this red dot right here. So this, in this representation, this red dot represents the starting point of your parameterization, and basically it is related to that very last comment I made in the previous part of this chapter, where basically I've told you that in order to prove that for any given Jordan regular curve you have at least a couple of anti-ortho-parallel points, if the maximum point of your distance function is on the border of your square domain, so basically if one of the two ends of you are considering is equal to A or equal to B, so it's at the very beginning or at the very end of your parameterization, then you can, in order to basically bring that point into this area, into these two triangular areas, you can change the starting point of the parameterization. So you introduce that number C, the magical number C, so that basically you translate the old function and you manage to bring the point associated to the original segment in the square domain, and so therefore you can define a gradient for that very point, and if that point is maximum, the absolute maximum, the gradient, if it exists, is necessarily equal to 0. So here I have an animation so that you can see in a much more evident way what's going on. So let's start the animation. As you can see, this red dot is now moving counterclockwise, and as you can see, the whole plot of the distance function is basically translating from here to here, following this direction, following the direction of the diagonal line. So the function itself doesn't change that much, like the main characteristics such as the number of maximum point, minimum point, and the overall shape doesn't change, but it basically is translated and it is moving around, so that if you have here a point of the graphic, of the plot, of the function, a point that is on the border, then by doing this translation, by changing the starting point of parametrization, this point will move into the triangular region, into the square domain, and you have no longer any problem. You have no problem in defining its gradient. So now I think I can stop the animation. Alright, and here I've written some more parametrization, but also for this very topic, as I've done for the previous topic and previous animation related to the spontaneous expansion of a cloud of repulsive charges in a sphere. Also in this case I'm going to attach to this video a trailer, a very short video, like 1 minute video, where you can appreciate and enjoy the animation and the distance function plot for 6 different curves, Jordan regular curves, and where you can basically enjoy it and see what's going on and the meaning of all the things I have told you. So I think this is everything for this third and last chapter. This was everything for today's project. I hope you enjoyed it. Let me know in a comment down below if you have anything interesting to say, and see you in the next project.